So let's move on with the rotational kinetic energy. To show that for an object that is rotating, we have a kinetic energy, let's consider the following object, which has an arbitrary shape, and it is rotating about the axis, z-axis, which passes through the point O. So let's consider this object as a collection of particles, and let's assume that it rotates about a fixed z-axis with an angular speed given by omega. Okay, that means that all the particles that they are moving with this object when it is rotating, with the same angular speed omega, of course. Now, let's consider that we have different mass elements that are given by M1, M2, M3, etc. And let's take one of these particles, the ith particle, to be defined by a mass Mi, traveling along the circle of radius Ri, where Ri is the radius of the circle traveled by the particle I, and that is the distance between the rotation axis, z-axis in this case, and the location of the particle. Okay, and of course we know that if this object is rotating, then this particle is moving with a given velocity v, and this velocity is always tangent to the circle traveled by or where the particle is moving. So for this particular particle Mi, we can define the kinetic energy as given by Ki is equal to half Mi Vr squared. So there is nothing new in this definition. هذا الشيء اللي بنعرفه من قبل نحن انه اذا عندكم particle ماشيه بسرعه معينه وعندها mass, then we can define its kinetic energy as the ratio half multiplied by m multiplied by v squared. طيب هلا الفكره انه هون عندنا نحن we have a rigid body, and this rigid body is made of some well, in principle infinite number of particles, but let's take it that for the moment we have n number of particles. So if we want to deduce the kinetic energy for this whole object, we have to sum up over I, where I it goes from 1 up to n, where n is the number of particles in this rigid body, of Ki. So it's the sum over I of half Mi Vi squared. Now we know that different particles, they should have different velocities. Why? I mean, let's consider a particle. Let's consider we have a particle here. This is not, so this is, let's say, mg or whatever you want. And so this particle isn't moving on the same circle as this one. So it's moving on a different circle, of course, which is, in principle, has a bigger radius than this mi. So let's call this mj. And the radius of the circle along which the mj is moving is given by, okay, I'm not able to draw a very straight line, but this is rj, right? Now, the speed of this particle is described, or it's given by vj, right? This is vj. The question now is vi is equal to vj? Okay. What do we know about the rotational motion? We said earlier in the very previous, in the very early slides, that if we have a rotating body, all the particles, they move with this rotating body. Each one is moving on its own circle. However, they are all making the same displacement delta theta. And that means that if the object is rotating with a given angular speed omega, then all the particles will be moving with this object with the same angular speed omega. However, their tangential velocities won't be the same. Why? Because if we consider the particle mi, we have vi is equal to, how v is related to omega? It's related to omega through the relation r times omega. احنا شفنا قبل شوي انه ال v هي equal لل r multiplied by omega. So vi is equal to ri multiplied by omega. Now the question is vi the same for all particles? Of course no. Why? لأنه ال Ri منها هي ذاتها بالنسبة لكل ال particles. If you take a particle over here, if you take the particle أقرب ل rotation axis, تكون عم تمشي على circle كمان بعد أصغر من السيركل اثنيناتهم الباقيين. So each particle has a different tangential velocity, because actually this tangential velocity is equal to r multiplied by omega, and the radius of the circle traveled by each particle is different than the other. فلهالسبب كل البارتيكلز بقلب الريجيد بادي عندهم نفس الانجلر سبيد اللي هي الاوميجا، بس ما عندهم نفس الفي، لانه الفي is equal to r multiplied by omega. So now if we substitute vi by ri times omega بنحطها كلها squared، بيطلع معنا انه الكاينتيك energy is equal to half times sum over I of mi ri squared times omega squared. Now الهاف ما بتدخل بالسم، it's a constant. الاوميجا كمان ما بتدخل بالسم لانه ما فيها اندكس I، هي نفسها لكل البارتيكل، فبيبقى عندنا half sum over I mi ri squared multiplied by omega squared. So this is the kinetic energy for this rigid body when making a rotation about the fixed z axis. And this quantity actually we called it the moment of inertia of the rigid body, as we are going to see in this slide. So the kinetic energy can be written as half I omega squared, and this I is what we call the moment of inertia of the rigid body. So نحن بنعرف كنا انه بحاله الترانسليشن كان في عندنا k that is equal to half times m times v squared. Okay, هون بحاله الروتيشن طلع معنا the expression of the kinetic energy as half times I times omega squared. So اذا ما نفترض انه الاوميجا مثل ما حكينا قبل هي equivalent للv, then we should expect that the moment of inertia I is the equivalent of m. And so the moment of inertia بهالحاله هون تلعب دور انه بتخلينا نعرف كيف الماس of this rigid body is distributed بالrigid body about the axis of rotation. اذا هي منها الماس، هي بتلعب دور الماس، وهي كمان بنفس الوقت بتخبرنا كيف الماس is distributed، كيف موزع الماس بالrigid body about the axis of rotation. So this is what we call the moment of inertia. Of course, this moment of inertia, it depends on the mass, it depends on the form of the rigid body, and also it depends on the position of the rotational axis. يعني إذا كان rotational axis هون، يعني الobject عم يعمل rotation about the axis passing through O، أو إذا كان الobject عم يعمل rotation about the axis passing through P، ما بيكون عنده نفس moment of inertia، بيكونوا مختلفين. Now, in general, when you have a system that is composed of a discrete distribution of masses، بيقدروا تكتبوا الاي بهالشكل هيدا. يعني مثلا اذا كان في عندكم سيستم بهالشكل، في عندكم 4 particles M1 M2 M3 and M4، وهول الماسز they are connected through some lightweight cord او lightweight rod pardon. فبهالحاله هون بنعتبره انه هيدا it's a discrete distribution of mass، وبالتالي بنطبق هيدي الاكسبريشن للمومنت اوف inertia. What if we have a continuous distribution of mass؟ بهالحاله مثلا لما كنا بنحكي عن سفير، سفير معبايه، او لما نحكي عن سيلندر، او لما نحكي عن رود for example etc. all these objects they represent a continuous distribution of mass. وبهالحاله بدل ما يكون في عندنا mi بيكون في عندنا infinitesimal mass element dm، وبدل ما يكون في عندنا summation بصير في عندنا integral. And so in this kind of cases we use I equals integral of r squared times dm to calculate the moment of inertia of these objects. And just as an example, here you have a table that shows the moment of inertia of some rigid objects. So you have, for example, a hoop, you have a annular cylinder, you have a full solid cylinder, you have a thin rod, you have a sphere, you have a hollow sphere. So you have different kind of objects. And here is another table also from our book where you can see more objects. So those are just examples of some moment of inertia of some objects. Now let's move on to the parallel axis theorem. We already said previously in here that the moment of inertia, it depends on the mass, on the form, and on the position of the rotation axis. Now, if your rigid body it has a simple geometry, in other words, if your object is one of these objects which is kind of easy to deal with, like you have a cylinder, you have a sphere, you have a thin rod, etc., it's very easy to calculate their moment of inertia, provided that the rotation axis, it coincides with an axis of symmetry. However, the moment of inertia about an arbitrary axis is not that easy to calculate. يعني إذا كان الأكسس منه الأكسس of symmetry، يعني إذا كان عم نحكي عن سفير for example، إذا السفير عم جيب المومنت of inertia يلي لها بالنسبة للأكسس يلي بارق بالسنتر يلي لها يلي هو an axis of symmetry، it's kind of easy to calculate this kind of or easy to calculate the moment of inertia about this kind of axis. بس لما يكون عندنا الأوبجكت منه كتير هين التعامل معه، بمعنى إنه ما في عنده axis of symmetry، وعم نجيب المومنت اوف انيرشيا اللي له بالنسبه ل an arbitrary axis. This problem is not quite easy to deal with, and this is why it's we often use a very famous and important theorem, which is given by the parallel axis theorem. So what does it state, this parallel axis theorem? If you have an object, a given object, okay, and you know the moment of inertia of this rigid object about an axis that passes through its center of mass, as you can see in this figure in here. So إذا أنتم بتعرفوا إنه هالobject إذا عمل rotation about the axis passing through its center of mass, you know what is the moment of inertia about this axis, which we call I center of mass. The parallel axis theorem, it states that the moment of inertia about an axis that is parallel to this axis and a distance d away from these axes, it's given by the following expression. So I, the moment of inertia about the rotation axis passing through O, is equal to the moment of inertia of this rigid body about the axis passing through the center of mass plus mass of the rigid body multiplied by d squared, where d is the distance between the two axes of rotation. And this is the perpendicular distance between the two axes of rotation. Now here we have a slide about the proof of this parallel axis theorem. I won't go through it. It's not very needed, but for those who are curious to know how we get this parallel axis theorem, you can go through the slide and then you can see how we did. Let's move on now to a new topic, which is about the torque. I will start the discussion about the torque by giving a very simple example. خلينا نحكي عن الباب. لما تجوا تفتحوا الباب، أي أسهل علينا نفتح الباب؟ أسهل علينا نفتحه من جهة اللي هو بيكون معلق فيه على الحيط، أو أسهل بكتير نفتحه من الجهة محل ما بيكون في مسكة الباب اللي هي أبعد، لما نبعد عن الأكسس أوف روتيشن اللي له. هيدا رقم واحد، أول سؤال. السؤال الثاني، ليش مسكة الباب بتكون على طول من الجهة المقابلة للجهة اللي معلق فيها الباب؟ So have you ever thought about these questions, for example? The answer is very easy. طبعا الأجوبة على هالأسئلة هي كالتالي. إذا ما نجي نفتح الباب كتير أسهل علينا أنه ندفش الباب من الجهة اللي بعيدة عن الأكس أوف روتيشن، يعني عن طرف الباب، عن أنه ندفشه من الجهة اللي هي مباشرة على جنب أكس أوف روتيشن، يعني محل ما معلق الباب. وهذا الشيء له أسباب معينة. طيب to discuss this case, let's consider a rigid body مثل بهالحالة هيدي. Okay, عندنا الأكسس of rotation, it passes through this point, okay, and you are applying a given force F, okay, trying to push this object. بكون تخلوا هذا الأوبجكت يعمل rotation about this axis of rotation through the application of this force F. Force F is applied at a point P, والvector position لها الpoint P, it's given by R. And to take the general case, let's consider that F is applied at the point P in a given direction with respect to the radial line، يعني عاملة angle phi مع الvector R. So لحتى ندرس and to understand how this force is producing at the end of the day a rotation for this object، خلينا نعملها decomposition into two components. خلينا نقول إنه في عنا واحدة من الcomponents اللي هي horizontal component that we are going to call it the radial component، اللي هي projection للF along the radial line or along the vector position of the point of application of the force. خلينا ناخد ال FT اللي هي perpendicular component أو ال projection لل F بشكل إنه هو perpendicular على هيدا الفيكتور R. Okay, so have a look here. ال FR اللي هي along the radial direction اللي هي الخط الحاملة هو نفس الخط اللي بيمرق بالاكسس of rotation. So actually this force, this component, it has no tendency to produce the rotation about the axis for the simple reason اللي هي انه it's line of action. يعني اللاين يلي حاملها يلي اذا بتعمل هون extension لهيدا الفورس pardon, هيدا اللاين بيمرق بالاكسس of rotation. So this is why we say that Fr does not contribute to the rotational motion and it has no tendency to produce any rotation in this case. While if you look at Ft لأنها هي perpendicular على ال R, okay, and the magnitude of Ft in this case it's F times sine phi, while Fr is F multiplied by cosine phi. So this component, it has a tendency to make a rotation. لهالسبب انتم لما تشدوا الباب من جهه المسكه انتم you are applying a force بشكل perpendicular على ال point of application of the force. يعني انتم هون مسكه الباب عم تكون هون الباب عم بيكون معلق. تخيلوا انه هذا هو باب تبعولكم. الباب معلق هون بالحيط بالنقطه O اللي هو الاكسس محل ما معلق الباب، وانتم هون عم تعملوا فورس. فمسكه الباب هي على الطرف، يعني هي عمليا على البوينت بي. لما تعملوا تشدوا الباب بالمسكه له انتم عم تعملوا you are applying a force that is perpendicular على الباب على الفيكتور R. And this is why الباب بيمشي بشكل اسهل مما اذا عملتوا force or you applied a force بمحل كثير قريب على الحيط. اذا عملتوا force هون بهالشكل هيدا حتى اذا كانت perpendicular اوكي مش نفس الافكت تاعتي. يعني بتحسوا انه انتم عم تشدوا اكثر بهيدا الجهه غير ما انتم تكونوا عم تكبسوا على الكبسه. اي نعم بتشدوا على جهه فتحه مسكه الباب عفوا. So this is why we need to define a new variable which we call the torque. So the tendency of the force, so this is actually the torque. The tendency of a force to rotate an object about some axis is measured by a vector quantity which is called the torque, right? So قد ايه هالفورس بتقدر تعمل روتيشن وتخلق روتيشن للاوبجكت. هيدا الشيء هالتندنسي بنسميها torque and it's defined in the following way. So اول شيء خلينا ناخذ هذا الاكزامبل اللي هو المفتاح. Okay, and you are applying a force F. So this is the point of application of the force موجود هون. This vector R هو ال vector position of the point of application of the force, right? وطبعا بنرسمه من نقطة الانطلاق اللي قلنا هي الاكسس اوف روتيشن، هي النقطة يلي مارق فيها الاكسس اوف روتيشن بالاوبجكت نفسه. So this is F. We can make a projection of F onto the line of I اللي هو هنسميه radial line. So we end up with F cosine phi for FR and F sin theta اللي هي perpendicular component للF بالنسبة للR. مثل ما كنتم شايفين هون ال F sin phi هي perpendicular على الR، أما ال F cosine phi هي collinear مع الR. Right? So we define the torque as depending on two main factors. أول شيء هي لها علاقة بالقوة اللي عم نشد فيها، يعني بمعنى آخر هي لها علاقة أو it depends on the magnitude of the component that produce the rotation، وأن ال component that produce the rotation هي ال Ft، فإذا هي لها علاقة depends on the magnitude of Ft on one side. كمان it depends on the distance between the axis of rotation or the pivot point and the point of application of the force. And so here, and the point of application of the force, I think it's gone because of the figure of application of the force. Of the force. And so this is why we need to define a new variable that we call the torque. It's denoted by the symbol tau, okay? And this tau is equal to the distance between the pivot and the point of application of the force on one side اللي هي ال R مضروبة بقيمة ال F نفسها، بس مش حيلا F هي ال component لل F يلي عم تعمل ال rotation, and so we are talking about F sin phi. And so actually this expression you can see it in two different ways. فينا نشوفها as ال distance R مضروبة بال F sin phi. So بهالشكل نحن شايفينها the product ما بين ال R, the distance between the axis of rotation and the point of application of the force multiplied by the perpendicular component of the force ft او بنقدر نشوفها as r sin phi multiplied by f وهال r sin phi okay it's nothing else than the distance d. هاي هي distance d اللي مبينه عندنا هون. هاد distance d is the perpendicular, the distance that is perpendicular okay ما بين ال point O where we have the axis of rotation and what we call the line of action of the force F. يعني هي الديستنس ما بين اذا بتاخذوا الفورس F وبتمدوا اللاين اللي هو حاملها اللي هي موجوده عليه هذا هو اللاين. So this line we call it the line of action of the force F. واذا بتنزلوا من النقطه O بتعملوا perpendicular على هيدا اللاين بيطلع معكم هيدي الديستنس دي. هالديستنس دي هي نفسها الار ساين فاي اللي شايفينها هون بالايكويشن. So this distance is called lever arm or moment arm. It is the perpendicular distance from the pivot to the line of action of the force F, and the line of action of the force F is an imaginary line that is extending out both end of the vector representing the force. يعني هو line يلي بنمده من خلال الفيكتور F وبنمد من الاتجاهين يعني من فوق ومن تحت. Okay, so this is what we use to define the torque. Usually the second one is more used. The second expression اللي هي إنه tau is equal to the force, the magnitude of the force multiplied by the lever arm, where the lever arm is the perpendicular distance from the pivot to the line of action of the force مثل ما شفناها هون بهيدا الإكزامبل. وكيف ما كان الإكزامبل اللي عم تحكوا عنه يعني أيا كان الأوبجكت. Let's consider that we have for example this cylinder. And on this cylinder you have this is the force for example acting on this circle or disc or يلي هو. So how do you and let's say that the object is making a rotation about this point for example. Okay, مش بالضرورة حتى يكون disc, you know. Let's take an arbitrary object. It has this form for example. And let's take this to be the point O where the axis of rotation passes. Okay. وعندكم هالobject it is applied open by this force F for example. اوكي كيف بدنا نعرف شو هي التاو او شو هي line of action of the force and the lever arm is very easy. You just take this line يلي بتمدوا اللاين يلي حامل الاف. So هيدي هي اللاين يلي في عليها الفيكتور F and then من البوينت O بتنزلوا perpendicular distance على هيدي اللاين. فهالperpendicular هي بنسميها هيدي هي الدي اللي عم نحكي عنها. So أيا كان الexample it's very easy to define the line of action of the force and the distance d which is the lever arm, and tau is nothing else than F multiplied by D. However, there is a more general form that we can use for the torque to define the torque of a force. And this expression is given by the vector product between the vector position of the point of application of the force and the force F itself. يعني بمعنى آخر, for any force F, إذا كان عندكم force F applied on a given object to make it rotating in a given direction. Okay, like for example مثل هون وهالobject إذا نقول في عندنا object بهالشكل وعم يبرم under the action of the force F. Okay, so you can define tau, the torque of the force F, as the vector product between R and F, where F هي الفورس نفسها أما ال R هي الفيكتور position للpoint of application of the force. يعني بتشوفوا when الفورس F عم تعمل where is it applied, where is it exerted, and then you make a vector between the origin اللي هو axis of rotation and the point of application of the force. The vector product between R and F is defined as the torque tau. So tau is equal to R cross F.